There you go.
Got it now? Great. Right, thank you very much. Apologies that I'm not actually there in person to be able to meet with you all today. I'm unfortunately in isolation, but I'm glad to still be able to join online. So the talk today is not a whole lot of science, but more. Sorry, is everything all right in terms of hearing me? Yeah, okay. It's more of a survey of what type of activity is happening in terms of paleoclimate modelling in the Australian community. So I've put this talk together with input from Katrin Meisner, Laurie Menville, Dave Hutchinson, Joe Brown, Nikki Wright and Georgie Folster. So thank you to all of them as well for their thoughts on the directions for paleoclimate modelling. So just to put a bit of context, this graph is from the most recent IPCC report showing atmospheric carbon dioxide concentrations in the top, global surface temperatures in the bottom, and showing those changes over the last 60 million years and out to 2300. And I just wanted to highlight this area, and this area in yellow is the area that we would most commonly focus on in terms of climate models. So from the 1850 pre-industrial through to 2100. But you can see that both in terms of past climates and also what happens beyond 2100, there's potential for much larger changes in the Earth system. And so that's where paleoclimate modelling comes in to provide additional perspectives that we can't get from that historical and 21st century interval. So some of the main questions that are important in terms of paleoclimate modelling and how paleoclimate modelling helps to move us forward in understanding climate. One of those is in constraining climate sensitivity, and through paleoclimate, we're able to look across a much larger range of past temperature changes. And so that gives us a much larger change to be able to try and tie down and improve our understanding of climate sensitivity, both through proxies and through paleoclimate simulations. There are also long-term climate feedbacks and potential for rapid or irreversible instabilities in the climate system. We know from the paleoclimate record that these have happened in the past. What we're not so sure about is exactly sort of at what point do we trigger these, and then some of those sort of really long-term implications of the climate changes that we're putting in place now. And so things like how do changes in greenhouse gas concentrations, ocean circulation, albedo, ice sheets, paleogeography, all of those types of things, how do they come into play once we start thinking about climate change on longer timescales? And then natural variability as well. So we know from the observational record isn't long enough to capture the full range of just natural unforced climate variability. So things like the potential range of El Nino variability, potential magnitude of droughts, and then also what their sensitivity is to external forcing. So just one example from the last millennium. This is some work that's just been accepted, led by Nikki Wright. This was looking at the southern annular mode, which when we reconstruct the southern annular mode using paleoclimate records, we get large pre-industrial variability. We typically don't see much pre-industrial variability in last millennium climate simulations. And one of the things we wanted to test with this was the potential role of solar forcing. And so in that lower panel, you can see in the red line, the magnitude of solar forcing that's traditionally used for forcing last millennium simulations. In the blue curve is a different possibility for the magnitude of solar forcing. And so what we wanted to see was what happens in a climate model if we run a much larger range of solar variability. And what we can see, these are some results using multiple last millennium runs using the Mark 3L model, using the regular magnitude of solar forcing in blue, 2 times the magnitude of solar forcing in green, and then that large amplitude solar forcing in purple. And what we see is that if we have a large magnitude of solar forcing, we do generate a lot more variability in the southern annular mode, and we get a much stronger correlation with our paleoclimate records. Where does paleoclimate modelling sit in terms of global climate modelling efforts? So in particular CMIP6, and we have PMIP4, the Paleoclimate Modelling Intercomparison Project, which is running in parallel with CMIP6. For some of the experiments that Australia has been contributing using ACCESS ESM 1.5, some of these are complete, some are still in the processing stage, but we've completed runs for the mid-Holocene, the last 1,000 years, the last millennium, and also the last interglacial. So what those runs are, the last millennium is a transient full forcing simulation starting in 850 and going through to 2014, which also has a large control simulation at 850 conditions. Joe Brown has run a mid-Holocene time slice simulation and is now looking at doing early and late Holocene time slices as well. There's a last interglacial run, so from 127,000 years ago. That's been led by Laurie Menville. There's been a number of publications come out of that already, and that ACCESS run has also contributed to some of the PMIP4 model intercomparisons as well. And there are also plans to run ACCESS ESM 1.5 for the last glacial maximum, and also for some high CO2 worlds, so going into the Pliocene, Miocene and Eocene as well. So just a snapshot from one of those model intercomparison papers based on the last interglacial. The top panel here is showing the ensemble mean for those paleoclimate simulations for precipitation change relative to pre-industrial, and the dots on there are showing information that we have from paleoclimate proxies. What you can see is a strengthening of the northern hemisphere monsoons, a weakening of the southern hemisphere monsoons in that ensemble mean. And then there's a bit of a model evaluation shown in the lower panel, showing how the different models are comparing with the information that we have from paleoclimate proxies. So the paleoclimate modelling community in Australia is using a number of different models and for a number of different reasons. So some of these are the GFDL CM 2.1 model. That's being used because it's considerably faster than ACCESS ESM 1.5, so it can be used for these runs sort of up to 5,000 years long. We've got the UVic and LoveClim models, which are particularly useful because they contain isotope traces, which allow us to, again, tie the model results in with paleoclimate observations to understand the processes going on. There's CSIRO Mark 3L, those results that I showed from Nikki Wright's work. And then also the CESM1, which has some large ensembles available. And just to show you, for example, for the last millennium, what's available to the community from CESM1. This is a summary of the last millennium ensemble. You can see the control runs and then these different full forcing and individual forcing runs. And just highlighted in yellow for comparison, this is what we've been able to produce so far with ACCESS ESM 1.5. So you can see the added utility that we get from also being able to go and look at these large ensembles, and that's something that's not possible to do yet with ACCESS. So in terms of a wish list for what paleoclimate modelers would like to see to be able to make ACCESS ESM more useful, the number one response from the people that I talked to before this talk was increasing the speed at which ACCESS ESM runs, and increasing the speed seems to come down to improving the efficiency of the atmosphere. That seems to be sort of one of the real sort of time sinks in terms of how expensive that model is to run. It's also something that generates a lot of data as well. So streamlining the process for converting the outputs of the atmosphere would help to save on storage and make it more efficient to run. Changing the boundary conditions and forcings is something that, if that was easier, that would enable a greater range of simulations to be run. So support for being able to set up change boundary conditions or set up different transient forcings, and access to the source code to help to perform these perturbation experiments. And also some sort of diagnostics, so a cookbook for standard output of the diagnostics from the ESM output, we think would be very helpful for being able to rapidly utilize the model output, but also getting a larger number of people in the community accessing and using those paleoclimate simulations. And then a wish list for additions that we think would make the ACCESS ESM an even more useful tool for paleoclimate research would be building in an ability for data assimilation, either online or offline, so that we can use the proxies and the models together rather than just sort of an evaluation, but use them to actually inform each other to get to better answers as to past climate changes. Isotopes and the ability to have offline traces would also help with improving the interpretation of paleoclimate proxy data, and building an ice sheet. Obviously, an ice sheet needs to be in a model that can run for a long period of time. So ESM, if it had that ability, that would open up a whole new avenue of research that could be done with ACCESS. And I'm looking forward to Felicity's talk later to hear her thoughts also on the ice sheet possibilities. So thank you very much.
Questions? Do you have questions in the room? Or questions online?
This is an online question. The ice sheet is often the cheapest part, I think. Sorry, it's a comment, not a question.
That's good to know. Yeah, I mean, it would be great to be able to have that capability within the ACCESS framework.
Yeah. Working? Is it working?
Yes.
Nerilie, it's super. Good talk. And you mentioned that the other models are faster. So can you say something about how fast are the other models, like the GFDI model and the CLEX-1, in terms of how many years can they compute per day or something like that?
I can't tell you that off the top of my head. I can tell you that the ACCESS ESM, we're getting about 16 years per day in terms of the runtime on that.
Any other questions? And after that, we should move to the next